So what we want to do today, we're going to go back to some graphs, and we're going to be on section 3.5. 3.5 is all about transformations of graphs, and I'm just going to show you one document. There's nothing that you really need to do with it. I just put it on your blackboard so we could look at it. And underneath section 3.5, transformation of functions, I'm on the course docs and links. There's a 3.5 parent functions PDF document. You can open it if you want. You don't have to. I'll flash it up on the screen here. These are what we call common parent functions in math. And you're going to recognize a lot of these, like a line. You've all seen a line. How do you make transformations on a line? You did it with all your marble slides, right? The transformations you can make on a line, you can up, down, left, right, and you can change the slope of it. So you could start with one line, and you could transform it into an infinite number of different lines. Change the slope, left, right, up, down, whatever. We've looked at absolute value a little bit. We did some absolute value equations. You guys might recognize this one right here, the greatest integer function. You see how it's like different steps? What activity did we do that had the step function? The egg, yeah, from the Desmos on the egg graph. You remember that one? We've looked at quadratics. So again, I could take that quadratic, I could slide it to the right, I could slide it to the left. I could slide it down, I could slide it up. I can make a quadratic get wider, like this, right? I can make it get really skinny, like that. And then, of course, you can flip it and make it open this way, down instead of up, up, down, like that. So there's all these transformations that you can make. So these are what they call the parent function. And then the transformed one, the different version of it, like if you move it left and shrink it or stretch it, or that's what they call a child function, if that makes sense. A child function is going to look like his parent function, but just be a little bit different, if that makes sense. Okay? So we are going to practice taking functions and transforming them, moving them around. And the function that we start with will probably be one of these. All right? And we're going to get to some of these other ones later in the year, exponential, logarithmic. We're not really going to get into the trigonometry ones, even though we kind of did when we did the graph of the, remember the merry-go-round and the Ferris wheel? Those gave us those wave functions, but we're really not going to get into trig in this class. So that document is just there for your reference. We're going to do 3 Desmos activities. The first one is called What's My Transformation? I'd like you to go to that one. I'm going to pull it up. So if you haven't figured this out yet, obviously I'm giving you points for completing these Desmos activities. But the whole idea of the activity is for you to discover something. You have a little aha moment. You go through a few activities and you're like, oh, that's what that means. Or that's how I do that. It's designed to make you think a little bit. So hopefully as we do these, you're not just doing them for the sake of, oh, I just need to get done with this so Jamie will give me my 5 points in the grade center. It's supposed to be a learning activity. Let me see if everybody's in there. So we are on What's My Transformation? Okay, so go ahead and get started. I'm going to monitor your progress. And like we've done in the past, I might stop you every once in a while. I might share a couple student responses, and we can talk about, good and bad things about particular responses. 2, 3, 4, 5, 9, 10, 11, 16, 17, 24. Some of the beginning ones are just kind of like playing around. So you can play around for a few seconds and then you can jump to the next step. And then when you get to number 3, they give you like a fake They made up the word parangula. That's not a real. Notice that didn't show up on our parent functions graph, right? But you can still get the gist of it, of the transformations with that. So some of you are already on step 6 or 7, but you did not successfully do step number 5. So go back and fix number 5 if you didn't do that. So what's the definition of successfully completing it? Well, you might get it really darn close, but the computer didn't think you got it close enough, so then it won't give you the check mark, if that makes sense. So when they ask you to get the black one on top of the orange one, try to get it as close as you can, as close as your eyeballs will allow you to do it. For example, I might do that. It's just not quite there, right? Flag me down if you're stumped and you want to look at something together. Eventually, they're going to ask you to summarize what you've learned in words. On number 8, they're going to say, take a moment and type a little sentence on what you just figured out. Number 7 is the one I want you to fix. You have one mistake in here. See if you can find it. So, yep. So you're going to start with which one? The dotted ones are the ones that you're trying to make, right? So it seems to me the orange one you got right. Your orange one is correct. But your blue, like, see here, blue dotted doesn't match your blue solid? Yeah, one more. So fix your blue, fix your green, and fix your red. Yeah, on step 7, it's color coordinated. Try to get like the orange dotted on top of the orange solid. Get the red dotted on top of the red solid, and so forth.
How do we get the green one so I come down here?
That's a good question. How do you? What do you think? So it's currently sitting where? Right in the middle and 0 there. So how could I take that whole thing and get it to move? How far do you want it to go down?
4.
4?
If I do it like that, it's 4.
And it moved it to the right. So try just f of x. Close your parentheses. Close your...
Oh.
There you go. And now try it. Oh, forgot the minus sign. See the difference?
Oh.
So one of them, notice that one of them, you did the parent function first and then subtracted 4. Whereas on all the other ones, you did the motion inside the parent function. There's a difference. It's an order of operations thing. Here, look at that. You just learned something. And now on number 8, you can type that in. I see a lot of check marks on number 7, which is great. That tells me that those of you that got a check mark on number 7 are spot on. If you got an X, that means you need to fix it. So notice all your other ones were left, right.
Yes.
This is the only one that's different, right? So instead of doing a plus or a minus inside the parentheses, try it on the outside of the parentheses. So just type in f of x and close your parentheses. And now try moving it down. Hit enter. Did it work?
Yeah.
There.
Thank you.
There you go. Yep. Jack, I think you need to look at your number 7. Go back to your number 7 for me, please. I think one of them was...
Yeah, it was.
Oh, did you just fix it now? Okay, thanks. Very nice. Lots of success on step 7. Yeah. So notice all the other ones were just sliding. This is the only one that's different because it's not a left-right, it's an up-down. So notice every time you slid it, you either added or subtracted inside the parentheses. Try adding or subtracting something on the outside. So type in f of x and close your parentheses. So that's your parent function, f of x. That's that one. Now try to subtract something. See how it's on the outside of the parentheses? There you go. Oh, except you got the wrong number.
Okay.
Try 4, I think. Perfect. Okay. Yeah. See how that one's different than the others?
Yeah.
Okay, I'm going to pause you for a second. I want to share with you Mackenzie, Noah, and Isaiah. I liked your 3 responses from number 8. This one I think was Mackenzie's. In order to move a graph sideways, left and right, you add a number inside the brackets to go left and subtract the number to go to the right. Parentheses seems backwards. Did anybody else kind of feel that way? Like, I want my thing to move to the right, so logically that tells you plus sign. But it's not. It's actually a negative sign, right? So if you think about why that is, if your graph, for example, let's say this is my graph. I'll just use a quadratic. Let's say this is my parent graph. All right? And I want it to be over here. We know that we're going to take our f of x and we're actually going to subtract some value. Let's say it's 5. We're actually going to subtract it to move it to the right. So if you think about why that is, if I just take, like, let's say this dot right here, well, I want that dot to move and I want it to be right there, correct? I want it to move 5 units to the right. Well, let's say this is 1, for example. So that would make this guy 6, right? Well, whatever used to be happening at 1, I now want it to happen at 6. So how do I get that to happen? If I enter 6, 6 minus 5 would give me 1. And whatever was happening at 1 would now happen at 6 because 6 minus 5 is 1. Does that make sense? It definitely seems backwards. But moving to the right means subtract. If I wanted to move it this way, I would have to add because I'm manipulating that x. I think, Noah, this was yours right here. If you want to move it to the left, x plus units. To the right, x minus units. But then if you want to move it up or down, then plus is up, minus is down. But what's the key? Notice Noah put it on the outside of the parentheses as opposed to inside the parentheses. And that was the difference with the green one in step 7. The green one was different than the other 3, right? Because you wanted to move it down, not left or right. And who was my third one here? Isaiah? Basically said the same thing. If you want to move to the right, subtract the number. Left, add the number. If you want to move your line up, add the number after the equation. That's the key. After the f of x. And subtract after the equation if you want to move it down. So, very good explanation. Some of the rest of yours were very good as well. I just picked those out. So, okay, I'll let you keep going. Which step are you on?
Number 11.
Number 11? Oh. So when you think stretch, there's 2 different ways to think of it. If you have this graph, one way to think of it is grabbing the left-hand side and the right-hand side and pulling it this way. That would stretch it, right? It would make it wider and shorter. Another way of thinking, so I can either stretch something this way and it'll flatten it out, or I could compress something this way and that would also flatten it out, right? So there's 2 different ways to think of it. If you want it to stretch, then you're changing the x, which would be changing it inside the parentheses. If you wanted to compress or stretch this way, then you'd be changing it outside the parentheses. So like the red one. Do you see how you were starting with the black one? I could either take that black one and I could stretch it this way to turn it into the red one, or I could squish it this way. Does that help? So try it each way. and see what happens. I think what they're shooting for here is what we call a vertical stretch. So if I'm looking at that black one, pick out reference points. This one looks like it's at, what, +1? And this one is at +3. So what multiplying factor changes a 1 into a 3? Times 3. Yeah, so I bet if I were to do that red one, I could go 3 times the f of x. And did I just do it correctly? Yep. I'm basically taking every output and I'm tripling it. Whatever the output used to be, I take it times 3. That's my new output. That's why it's stretched out. Notice that number 12 is another summarize your thoughts. I'm going to pause you for 1 second again. On step 11, everybody take a look at their step 11. Oh, you can't because I paused you. Which one was different? The blue one, right? And I typed in my answers right there. And a lot of you figured this out in number 12. Notice that the blue one is different because I put my multiplier on the inside of the parentheses. So I was multiplying x, the input, times a fourth or 0.25. And then after I was done manipulating x, then the f of x took place. The parent function came second, right? Versus the other ones, f of x was unaffected. We could do f of x and then times 3. Okay? So if you can get this order of operations in your head, where sometimes we do something to the input first, like add, subtract, multiply, or divide to the x, that's going to affect us in some horizontal manner. And then the f of x takes place, whatever the f of x is, if it's a quadratic or a parangula or whatever our parent function is. Okay? Versus sometimes we do the f of x first, and then we do something to it after we're done with the f of x. Add or subtract to make it go up or down, multiply it times something to stretch it up or down. A lot of you had good suggestions. I picked out Megan's. I thought you said it well. When you have a number in front of the f that's on the outside, right? So we're going to do the f of x and then multiply it times something. You're stretching it up and down. And when you add the number in front of the x before on the inside of the parentheses, then we're stretching it somehow horizontally. Now remember, a stretch can be taking something and making it taller and skinnier. But if you multiply times a number less than 1, like 0.5 for example, that would be like cutting the height in half. So it's hard to wrap your brain around sometimes, but sometimes a vertical scrunch, if you will, has the same effect as a horizontal stretch, if that makes sense. You guys are doing very well on this activity, by the way. Okay, I'll let you finish it off. If you've already finished, there's a really short Desmos that we are going to do second, and that is the one called card sort transformations. So if you're done with this one, you go ahead and work on card sort transformations. Step 13 is fun because now you have to do a combination of both. You're sliding it up, down, left, right, but you're also doing a stretch. So you're doing more than one transformation. as you're working on that number 13, some of you might be able to cut to the chase and enter the whole equation all at once. But what typically would happen is you try something, oh, I'm really close, I'm going to adjust it a little bit. Oh, now I'm a little bit closer, I'm going to adjust it again, adjust it again, adjust it again. And after you do it 4 or 5 times, you can hone in on what you're actually trying to do. You two might have a mistake on the second to last one. Check it out.
Oh my God, really stop.
Wait, C3? I'm literally
No, it's not. I'm not doing it.
For those of you working on the card sort, I believe that you have to group 3 cards together. 2 graphs and a equation. Does that sound right for those of you that have already done it? 2 graphs and 1 equation. That's the group of 3 you're looking for. And we're going to talk about the end of the first one here in just a minute, but I'm going to let a few of you finish first. Even if you're not done with step 13 yet, go ahead and jump to step 14, because I want you to answer step 14 so then we can compare answers. So go ahead and do that now. You can always come back to 13 and finish it later. So here's how you guys have voted. If you look at 2 students thought Malcolm was right, 1 student thought Jamal was right, and 19 of you thought both of them were right. They're both correct. Who can explain that? I got to read the original question again. If you vertically stretch something by -1, then every output value is going to become the negative of himself, right? So for example, this point right here is +1 height. If I take +1 times -1, I get there. This one is +5. If I take it times -1, I get right there. So what is a -1 multiplier? It's a reflection over the axis. What happens if I would have put a -1 multiplier on the inside of the parentheses? Then I would reflect this way, right? Over the y-axis. Okay, go ahead and finish this one. And the card sort, we'll go over that on Wednesday. I want to direct your attention. I'm going to push pause on this really quick. I want to direct your attention to the board and the function that I wrote up here in marker. So my first question here is, can you identify this guy's parent? So you guys have seen it before when somebody says, oh, you look just like your dad, or you look just like your mom, or you look just like your brother, or you look just like your sister. Well, this guy looks like somebody. And specifically, I'm asking for his or her parent. Who's the parent? Anybody? Yell it out. It's a parabola, which is what kind of function? It's a quadratic. Can you guys peel off all of the can you kind of peel off all of the transformations and just see the parent function? The parent function would be x squared. Just a regular parabola that looks like this. Let me get my font size a little bit bigger. That would be the parent, x squared. But now look at all the things that are happening to the parent. We're changing the parent into a child, right? What's the very first thing? Do your order of operations. Look at x. That's our input. What's the very first thing that happens to x? We add 6 to them. And if I add 6, ignore the -3 and ignore the -7 for a second. If I add 6, where does that move it? To the left? 6 units, correct? So if I go like this, and I say x plus 6 squared, see how I just moved them to the left? So there's one of my transformations. Okay? After the x plus 6 happens, then we know, then is the squared, order of operations, right? We do the parentheses first, then the squared. Well, the squared is the parent. So now the parent has happened. So everything that happens from here on out is not going to be left, right. It's going to be up, down. Which one happens first, the 7 or the 3? The 3. What's it going to do to the graph? Just the 3 alone is going to make it go this way, tighter. It's going to stretch it times 3, right? So let me put in a 3 out front here. That stretched it up. The negative is going to cause me to do what? Flip it down. Negative. Flipped it down. So now we're way down here. And finally, what's the -7 going to do to me? Move it down 7 units. And now my final graph is way the heck down here. So that had a lot of transformations on it, but it still looks like his parent, right? It's still a quadratic. Okay, so the only thing I want you to accomplish for next time is finish that card sorting Desmos, which some of you are already done. And then you should be able to take a stab at your 3.5 quiz. And we'll finish up some more thoughts on 3.5 when you come back on Wednesday. Okay, see you then.